Hello everyone and welcome to webinar number 130 brought to you by OBE Energy. Presented to you by Engineer Safe. Engineer Safe Sharab, who is a customer success engineer at NOV, specialized in real-time monitoring and drilling performance optimization, with 5 years of experience in drilling operations, including 2 years as a drilling supervisor at Babetco and Chiron Energy IV. I will take some of your time to discuss with you our OBA's upcoming services and plans. If you are interested in today's webinar or topic, you can register in the drilling problem causes and solution course starting 19th of July, inshallah. It will be for 1 week, presented by Engineer Saif Shalabi as well. This if you couldn't the If your time was not available, it will be recorded and presented to you through our website with a bunch of other recorded courses, inshallah. You can have a comprehensive curriculum, flexible learning, and expert instructor, inshallah. You can also check OBA's App Store, which contains affordable alternative for softwares, Excel add-ins for specific tasks, resolved to save time and money. You can also check out OBA's mentorship program, where you can select a topic which you can talk about with one mentor. It's only you, one-on-one with him. It's a highly experienced mentor, tailored based to your needs, and it can also contain explaining how to know softwares or some parts of it, practicing how to produce output results from a software, guiding personal data or mentor, professional guiding for PhD and master, and so on. All of this and more is available on www.com. You can become an ambassador with OBA through two main tracks. The first one is joining one or more courses or taking the mentorship program. Thank you for your time. Engineer Safe, you can take it from here.
My voice is clear?
Yes, it's clear, engineer.
Okay, 1 second. I will share my screen. My screen is now available.
Yes,
You can...
engineer is available.
Okay, perfect. Good evening, everyone. Welcome to our free session, Drilling Problems, Causes, and Solutions. Before starting, I would like to give you a brief about me. I am Saif Shalabi. I am a customer success engineer at NOV. I'm specialized in drilling performance optimization and real-time monitoring. I have worked as a drilling supervisor for Papetco, and I have also worked as a workover and well completion engineer. I have plus 5 years of experience in drilling operations. You can see on the bottom of this slide my WhatsApp contact information in case you wanted to ask me anything about this session or in drilling operations in general. Our presentation today is going to include all these drilling problems. We are going to start with stuck pipe. Then we are going to move to downhole losses, bit bowling, string wash out, twist off, nozzle blogging, drill string vibrations, ballooning, and eventually well control problems. We are going to define each one of these problems. Then we are going to discuss their causes, how we can detect them, and how we can troubleshoot them. Our first half of the session is going to mainly include stuck pipe and downhole losses. Then in the other half, we are going to briefly discuss the other problems. At the end of this session, there will be a Q&A part through which you can ask any question you have. Starting with the first problem, which is stuck pipe. In stuck pipe, we have two major reasons or two major types of stuck pipe. The first one is the mechanical sticking. In mechanical sticking, the pipe is physically obstructed by an object or by the formation itself. Why the second type, which is differential sticking? Differential sticking is not like mechanical sticking in being physically obstructed, but it's more like being sucked into the formation. The problem is that we have a differential pressure where our hydrostatic pressure is higher than the pore pressure. This differential pressure causes the drill string to be sucked into the formation. We are going to know each one of these in more details in the next few slides. Mechanical sticking has many reasons, starting with the first reason, which is pack-off. Pack-off is mainly cuttings accumulation. Due to bad drilling practices, due to bad hole cleaning, we have accumulation of drilling cuttings which surround the drill string, causing it to get stuck. The second cause is due to well bore geometry. This is due to the main path or the path of the well bore itself. It may be due to one of these three reasons, starting with key seating. Key seating is the formation of this micro hole next to the main well bore. This micro hole is formed due to sequence of soft and hard formations or due to severe dogleg. This severe dogleg or this sequence of soft and hard formations may cause the BHA to be pushed aside to the borehole or to the main hole, causing the boring of a side or a micro hole. When we start pulling out of hole, when the tool joints which have higher or larger OD start to pass through this micro hole, it may get jammed into it, causing it to get stuck. Second reason for well bore geometry is ledge sticking, due to irregularities in a well. These irregularities form ledges that may cause the drill string to get jammed into one of them, either while running hole or pulling out of hole. The third well bore geometry cause is the tight hole. This is mainly caused by undergauged bit, causing the drilling of the hole to be of smaller size than the calculated or the planned. When a large OD part or a large OD section like stabilizer passes through this restriction, it may cause it's stuck in this tight hole. The third reason for mechanical sticking is formation instability, and it may be due to more than one reason as well. Starting with bridging and caving. Unlike cuttings accumulation is due to poor hole cleaning as we discussed, but bridging and caving is because of insufficient hydrostatic pressure. This insufficient hydrostatic pressure can't support the borehole walls, causing them to start bridging and caving into the well, causing it to form these cuttings, the same as what happened in the pack-off, and hence causing the string to be stuck. It may also be due to swelling and sloughing, which is a main characteristic of formations like reactive clay and reactive shale. If they are not properly inhibited, it will start to swell and to slough into the wellbore, causing stucking of the drill string. Also salt healing, which is a property of salt formations, also called creeping, where salt starts to heal and creep into the wellbore once drilled. This problem doesn't only cause mechanical sticking, but also cause other problems later after drilling, like casing collapse, for example. All these reasons or all these causes can be counted as physical obstruction to the string. The string has been physically stopped by a specific object, whether this object is formation, cuttings, or tight hole, or any of these reasons. Moving to the second type of stuck, which is differential sticking. As we discussed before, it's because of differential pressure. Differential pressure between the well bore and between the formation, causing to push the string to the side of the formation and getting sucked into it. What affects differential sticking is three main factors. The first factor is the overbalance, as we said. The overbalance has two subfactors that are affecting it: the hydrostatic pressure inside and the pore pressure on this side. So if we want to know how much overbalance we've got, we need to calculate both of them. The hydrostatic pressure, the famous equation in the oil and gas, is 0.052 times the density in ppg times the depth in feet. And the pore pressure can be estimated from offset wells or from geomechanic models and so on and so forth. The second thing that affects differential sticking is the contact area. The more the contact area is, the more this string is going to be sucked into the formation, the higher the severity of the differential sticking. And this is why in some high differential sticking tendency wells, we tend to use spiral instead of slick BHA. This spiral BHA or this spiral coolers have grooves, helical grooves inside the cooler, which causes these grooves to be not in contact with the formation, and only the visible part, which is this thin helical part, which is going to be in contact with the formation. So this decreases the contact area and hence decreases the differential sticking probability. The third factor which affects differential sticking is time. Time is your enemy in differential sticking cases because we have this equation which represents the amount of force that you will require to pull a drill string out of a differential stuck situation, and it's equal to delta P times A time mu T. The delta P is the overbalance that we talked about. The A is the contact area, and the mu T is what is called coefficient of friction. And the reason why there is T between brackets because this coefficient of friction is dependent on the time. The more the time is, the higher the coefficient of friction, the higher it is to get free from a differential sticking scenario. How we can know that the stuck pipe event happened? We have multiple types of stuck pipe events and we have multiple causes. So we will need to make some diagnosis between them so that we can know what kind of stuck pipe we are suffering from or what kind of case we have so that it will reflect our future or our next steps for troubleshooting. We agreed on back off, both Willport geometry and formation Willport geometry and formation instability and differential sticking. These three first types are the mechanical types, and this differential sticking is a type on its own. All the four of them have one common thing, which is the movement after. All of them, you will not be able to move the string, and you will not be able to rotate the string. So this is the common symptom between all of them. How we can differentiate between them? We can differentiate between them using circulation and the kind of movement that happened before the stuck event. For both the differential sticking and the Willport geometry, most probably you will find that you have full circulation. But in case of backoff and in case of formation instability, most probably you will not have any kind of circulation, or even if you have, it will be severely restricted. So this is the first thing to differentiate between these two and the second and the fourth type. Going to the movement before. When it comes to differential sticking, it happens only when the string is in static conditions. So if you have been in static conditions, followed by stuck scenario, while you have full circulation, then you definitely have differential sticking scenario. However, if you have full circulation, but you were in movement before you got stuck, then you got stuck due to Willport geometry. When it comes to backoff and formation instability, you will find that it's dashed. This is because it can happen in both cases. It can happen in both movement or in static conditions. You can also see the same reasons that we discussed on the right. The backoff is mainly due to poor hole cleaning and bad drilling practices. The Willport geometry is due to severe dogleg and hard soft formations causing key seating and ledges, also due to undergauge bed causing tight hole. For the formation instability, it's caused by reactive shale causing swelling or sloughing, and insufficient mud weight causing caving and creeping effect, which is associated with salt formations. And when it comes to differential sticking, we know that it's due to high overbalance and due to high contact area, which is provided by either large OD BHA or thick filter cake. After knowing how we can differentiate between the different types of stuck, we need to know how we can prevent it in the first place. We can prevent it using these four main steps or these four rules of thumb. The first one is drilling parameters, second one mud properties, third one cleaning sweeps, and finally BHA design and stiffness. And we will discuss each one of them in the next slides. Starting with the drilling parameters, you need to optimize these three drilling parameters so that you can reduce your probability of sticking. The first one is gallon per minute, which is related to flow rate. The second one is RPM, or revolution per minute, which is related to rotation. And the third one is ROP, or rate of penetration, which is obviously related to penetration rate. For the gallon per minute, we need to follow a general rule of thumb if we don't have like a roadmap or a specific procedure from the operator company. This rule of thumb says that the gallon per minute needs to be from 40 to 60 multiplied by the hole size. So let's suppose that we have 17.5-inch hole. If you multiplied it by 40, we get 700. This is the minimum gallon that you need to keep in surface hole to keep hole cleaning in good state. And if we multiplied 60 by 17.5, then we have 1050, which is the maximum or the highest boundary of a good hole cleaning in 17.5-inch hole. This is a rule of thumb in case you don't have specific procedures from the operator company. When it comes to RPM, you need to maximize the RPM that is allowed by the roadmap, which will not cause any damage to the drill bit or the drill string, and which will not cause the happening or occurrence of any drill string vibrations. When it comes to ROP, we need to control the ROP so that the generated cuttings are not higher than the cuttings expelled by the circulation out of the hole. We need to generate less cuttings than the cuttings that are exiting the well. On site, there are some simulators that are used by third-party companies. These simulators calculate the cutting load based on the parameters that you are using. So you are feeding the ROP, you are feeding it with the gallon per minute and the RPM. Then the simulator calculates the cutting load that you have in the well. As a rule of thumb, you need not to exceed 3% of cutting load in the well. Otherwise, you are going to accumulate cuttings in the well. You are going to have severe effects when it comes to stuck risk. Second way through which you can prevent stuck pipe event is through controlling mud properties. First mud property that we need to control is the mud weight. The mud weight helps you to reduce the probability of differential or mechanical sticking through two ways. The first way is through supporting the borehole walls, which prevents caving. The second way is because as mud weight increases, the buoyancy effect increases, which helps to keep cuttings in suspension and help to carry them and lift them to the surface, especially in deviated and horizontal wells. Second property is the rheology. The rheology includes many factors, but the most important ones are the yield point, the plastic viscosity, and the gel strength. The yield point is a good indicator. We need it to be high within a specific range because it represents the carrying capacity of the drilling fluid during circulation. The plastic viscosity is not favorable because it represents the solid content in the drilling fluid. And the gel strength is favorable to be flat gel. A flat gel is a gel which can fast or rapidly establish gel property and rapidly break this gel. Why we need this behavior? Because when a gel behavior is easily established, once you stop circulation, your drilling fluid will be able to suspend cuttings in static conditions. And when you start circulation, this gel can be easily broken, which will not cause any surge pressures to your formation, and hence it will not cause any kind of fracturing to your formation in case this surge pressure was or contained high spike or something. The third property, and I would like to just discuss this one with the fluid loss because both of them has the same effects. When we have high solid content and high fluid loss, both of them reflect the thickness of the filter cake. As solid content increases and as fluid loss increases, the thickness of the filter cake increases, causing higher probability for differential sticking. Finally, the inhibition. we need to maintain inhibition in clay and shale, especially reactive clay and shale zones, so that we can prevent its swelling and sloughing and hence protect our drill string from getting stuck in these formations. Third way through which we can prevent stuck pipe risk is through cleaning sweeps. A sweep is a pill that you pump in your drilling fluid to do a specific function. In this case, the cleaning sweep, as the name implies, involves cleaning the cuttings on the bottom or in the well so that you can enhance your whole cleaning and you can resume operation without a high risk of stuck pipe. In case we have a vertical well bore, it's favorable to pump high vis sweep, which is short for high viscosity sweep. This is a sweep that just has higher rheology so that it can clean the drilling cuttings better. While in case we have inclined or horizontal wells, we pump what is called tandem pills. And because it's called tandem, it's more than one pill. It's not just one pill. It's two pills in one pill. These two pills are pumped consecutively. The first one is low vis sweep, and its effect is to cause disturbance because this disturbance or this turbulence causes disturbance to the cutting bed in case of we have high angle well bore or horizontal well bore. The cuttings tend to rest on the low side. So when we pump this low vis sweep, it causes turbulence and hence causing disturbance for this cutting bed into the drill string or into the drilling fluid. Then we pump after it immediately high weighted bell so that it has high buoyancy and it can carry these disturbed cuttings to the surface. The fourth way through which we can prevent stuck pipe is through BHA design and stiffness, mainly by decreasing the contact area, as we discussed before, by using these spiral coolers instead of stick coolers so that we can reduce the point of contact or the area of contact. We can also optimize BHA so that it can give less stiffness and hence less susceptibility to well bore geometry stuck. We can also run BHA that has reamers so that it can enlarge the well bore after the bit so that it can prevent the occurrence or the happening of any kind of key seats or tight holes. Finally, if you drilled an original hole and for some reason you had to pull out of hole and to run in hole with a new BHA, then try as much as you can to keep the same configuration because each BHA has a fingerprint in the formation. And when you run in hole with a different BHA, this fingerprint is different from that fingerprint. So when you run in hole with this BHA, it may get jammed into one of the ledges of the original hole. This is why you need to keep things similar in the same hole. Now, after knowing how we can reduce the probability of sticking, what will happen if we got stuck? How we can get out of this situation? First of all, you need to identify the type of stuck because it's going to differ how you are going to react with it or how you are going to troubleshoot it. In case you have a pack of scenario, then it means that you don't have circulation. All the circulation path is blocked. So if you kept circulation, your pressure is going to spike and it's most probably it's going to break a formation below the pack off. This is why the first action you need to take is to stop the pumps, shut off the pumps, and bleed any trapped pressure. After that, we need to re-establish circulation. But as we said, we don't want the pressure to spike. So we are going to gradually increase the pressure. Even if you have to operate your pump at 1 stroke per minute or 2 strokes per minute, but you need to keep a low pumping pressure trapped, which is from 200 to 400 psi. So let's say that you placed 400 psi trapped pressure in your string, and then it started to decline. It declined to 250 psi, for example. This means that you are creating pathways. You are creating path for the drilling fluid to start getting circulated, which means that you are getting free. This is why if the trapped pressure that you placed has dropped, increase the pump strokes so that it raises again to the 400 psi and keep this 400 psi all the time. While keeping this 400 psi, start to work the string. But before working the string, you need to take a mark so that you can know the progress you are making at each trial you work the string with. So you will place the string in the neutral position and take a mark, a physical mark with any kind of pen on the rig floor on the drill pipe. And once you do this, start working the string while holding this trapped pressure in the side of the drill string. How you can work the string exactly? It depends on the direction before the stuck. If you were pulling out of hole, then you need to work the string down. If you were drilling, then you need to work the string up. Why is this specifically? Because let's say that you got stuck while you were pulling out of hole. This means that this tight spot or this troublesome zone that you got stuck in lies upward. So if you started working the string upward, you are increasing the jamming into this troublesome zone. You need to get out of it. So you need to get away from it. This is why you work the string in an opposite direction to where you got stuck in the first place. So working the string here, let's suppose that you got stuck downward, so you are going to work the string upward. You need to start jarring in a direction opposite to the stuck, which is in this case upward. After activating the jar, you need to reach the maximum allowable limit that you can apply on the string. This limit is 80% of the maximum tensile strength, because this other 20% is a safety factor. You can, of course, increase above the 80%, like 85 or 90, but it requires approval from the operating company. But the 80% is the safe envelope here. So this is a trial in working the string up. If you are going to work the string down because you got stuck up, then you have another option that you can make. You can trap pressure, and not only pressure, you can also trap torque. Torque cannot be trapped while working the string up because it may cause twist off. But if you are working the string down, you can apply trap torque. So in this case, if you are working the string down, trap the maximum torque and start to work the string down with the same exact steps. Start jarring down, then reach the maximum allowable limit while working down, which is 100% of the slack of weight, because now you are not afraid of any kind of failure under tensile mode, because you are not in tensile mode in the first place. So if you tried to do all these steps and it failed to get free, and the decision is going, and by the way, the trial is not one time or two time. Sometimes on the rig, you try to work the string 6 hours or even 12 hours. You work the string for a long time unless you get no further progress. This mark that you have taken in the first at the beginning is not changing. It's not getting up or down, which means that you are on your same place, which means that you are heavily stuck and you're not going to get out of it. Once you reach this decision that you are not going to solve this stuck and that you need to port the string, then start to make a trial in the same direction of the stuck. I know that we said we will not try in the same direction, but in this case, you already are going to port the string. So you have two case scenarios. Working the string in the same direction of stuck and it worked, then you have saved a lot of time and a lot of money and a lot of MPT. But if it didn't work, then you didn't lose anything because you already were going to port the string. So if you reached the decision that you are going to port the string and start fishing, start first to work the string in the same direction of stuck because it have a probability of working. In case we have a mechanical stuck in these two formations, we have also extra option that we can do while working the string, which is pumping acid in case of limestone and pumping fresh water in case of salt formation. Because limestone is soluble in HCl, and obviously salt is soluble in fresh water. So this can dissolve the formation that is surrounding the stuck point. In case you have the differential stuck, then you don't need to apply the first steps that we applied here because you already have full circulation. So you don't have to start staging the pump and these first steps that we talked about. So you will just immediately start with working the string. The right direction to work the string is downward in this case. In differential stuck, it's better to work down because you will have option to trap torque, and this trap torque may help you to free the direction. So you hold or you trap torque and you start working the string as we did before. You can also have two additional features or two additional options that you can apply here in case of differential stuck that can help you to get free, which are either to decrease the mud weight, but you need first to make sure that it's not going to subject you to will control situation. And you can also pump what is called pipe free pill. This pipe free pill can deflocculate or cause drying and cracking of the filter cake so that you can get free from it. Again, if all attempts failed, make trials to work the string up because you are going to board the string and fish it anyway. So after troubleshooting the stuck, you have two scenarios. The first one is if it got free, and the second one it's not free. So the first case, you got free, you saved a lot of time, you saved a lot of MBT, you saved a lot of money, but you need to beware because you may get stuck again. This is why after getting free, you need to maximize the rate, circulate with the maximum rate, rotate, and keep working the string so that you will not stuck again. Then you need to ream and back ream this section to prevent any kind of tight spots to cause you to stuck once more. Then you need to circulate the whole clean. Why is this? Because in many cases of stuck, you can't establish circulation. And by not establishing circulation, all these cuttings above the stuck point are going to start settling around you. This is why you need to just clean the hole from all these cuttings that has accumulated while your pump was not on. This is why you need to circulate the hole clean. Afterwards, you can continue with normal operations. However, if the string is not free, then we will need to port the string and start fishing. But this must come with a specific sequence. First of all, you need to specify the place of a stuck, which is done by free point indicator. Free point indicator work on the concept that it can give you readings different. It can give you readings of the parts which are under tensile load, different from these parts which are not under tensile load. Since all the drill string here above the stuck point is under tensile load, while the part which is at the stuck is not carried by the string, but it's carried by this stuck, so it's not subjected to tensile load. This is where the reading of the free point indicator is going to be different, and this is how you can know that this is the stuck point, so that you can start working above it. And by working above it, you can back off the string from the connection above the stuck point, and this is done by heating on the connection and start applying torque, applying rotation in the direction of the breakover while pulling upward. If you failed to pack off the string, you can start to use severance tool, which can cut at any part of the pipe body and retrieve this free part. Then the part which is left in hole can be retrieved with fishing operations. However, if your fishing operations attempts were not successful, you will have to either go to milling or to sidetracking, or even eventually plug and abandon the well. So that was our first problem. The second problem is downhole losses. Downhole losses can be classified into four major categories. The first one is the seepage losses. This category is less than 20 barrels per hour, and mostly it's manageable. You can keep your normal operations while you have seepage losses. The second type is partial losses, which is from 20 to 100 barrels per hour. And this type is harder to manage and it requires curing. The third type is severe losses, which is higher than 100 barrels per hour. This type must be cured so that you can continue normal operations. Finally, the worst part is the complete loss. The complete loss will prevent you from having any return on the surface. And the main problem here is that you keep generating cuttings with no cuttings exiting out of the hole. So you are just generating cuttings which may even increase the severity of the situation. This is why this kind of losses must be cured before continued drilling. The causes of losses are many. They may be due to nature, or due to the formation behavior, or it may be induced. In case of the formation, it may be due to high porosity or high permeability and unconsolidated formations, like the surface holes in the Western Desert of Egypt, or it can be due to fissures, due to vugs, due to caverns. It can be due to some fissures that exist in the formation downhole. While the induced ones are due to bad drilling practices. And by bad drilling practices, I mainly mean high ECD. ECD is short for equivalent circulating density, and it is two main parts. The first part is the hydrostatic density itself, or the mud density due to hydrostatic pressure, and the second part is the pressure losses due to friction, which is the annular pressure losses. By combining these two effects, we get ECD, which is higher than the actual mud weight. So if the ECD is high enough, it may cause extra pressure on the formation, causing it to get fractured. So you think that you have 9 ppg mud, then you are just subjecting your formation to, for example, 4,000 psi, but actually your mud is not 9 ppg, it's 9.5, and it's subjecting the formation to a higher pressure due to this ECD part that you didn't count. The reason why losses are very dangerous problem is that because it's an entrance to many other problems. So the worst problems that can happen on a rig are wellbore instability and stuck, or well control problems. And both of them can be induced due to losses. Because by decreasing the hydrostatic head, you are subjecting yourself to lower hydrostatic head, and hence you subject yourself to a higher pore pressure than the hydrostatic pressure and getting an influx into the well. And also by decreasing the hydrostatic head, the mud will not be able to hold and support the walls of the well, and hence it will cause some caving to happen, and it increases the probability of stuck conditions. This is why you need to detect losses as soon as possible and start curing it. The way how we can detect losses is simple. You can just monitor the bed volume. If you found the bed volume decreases with time, then this means that you have losses. Also, it's visible by other ways through which the pump pressure. If you found decrease in pump pressure, this means that you may have losses, because you have a tight system of circulation. If you started creating fractures in it, then the pressure will start to drop. The same exact way when you have a pressure in a surface line, and this surface line has a leak, you will find the pressure drop. This is the same exact thing. The fluid will start to leak into the formation, causing the system to be not so tight and hence to drop the pump pressure. Also, you can see visible losses at the flow line and decrease in flow return. But this is more obvious in case of partial and severe losses, not in case of seepage losses, because it may not be so visible when it comes to flow return. And of course, in case of complete loss, you will not even find any kind of return on the surface. How we can mitigate and treat losses? It depends on the kind of losses. If it's natural losses due to formation behavior, then you need to use LCM, which is short for lost circulation materials. These are materials that are used to go inside the channels and the pores and the fractures in here and causing them to be plugged. They are of different sizes and of different shapes. This is why you need to make sure to use a blend of these shapes and these sizes so that it can plug all kinds of fissures and pores. However, if your losses are induced, then even if you cured it with LCM and you kept the same drilling practices, this will cause again more fissures and more fractures to happen, and you will have more losses. So you need first, before pumping any kind of LCM, you need first to control your drilling parameters. And this is done by reducing the ECD, which is the equivalent circulating density that we discussed before. And as we said, it's composed of two major parts, the hydrostatic part and the dynamic part. The hydrostatic part is dependent on the mud weight. This mud weight can be reduced unless it will cause you any kind of well-controlled situations. And also you can control the ROP because the ROP generate cuttings. And if these cuttings generations is very high, then you are filling your analysis with cuttings. These cuttings is going to increase the actual density of the drilling fluid because it's not going to be the same that you see on the surface. It's going to be more because it's full or loaded with cuttings. While controlling the dynamic part is by controlling friction. And this is done by reducing flow rate and mud viscosity. But be careful because if you decrease both of them under a specific threshold, then you will start to have poor hole cleaning. And if you have poor hole cleaning, again, you will have cutting load in your annulus. And instead of decreasing the ECD, the increase in the hydrostatic part is going to be more than the decrease in the dynamic part. And hence, the overall is going to be an increase in the hydrostatic pressure and an increase in the ECD. However, if you try to reduce ECD for induced fractures or induced losses and you used LCM, but the problem is not solved, then you will have to go to more critical or more complicated solution, which is the cement block and the advanced builds. These builds and this cement blocks can be used to completely seal the thief zones so that you can complete or continue in your normal operation. Next problem is bit bowling. After this problem, we can take a short break for only 5 minutes and be back. So the bit bowling is mainly the aggregation of sticky cuttings on the bit face, causing this bit face to be covered, and and the cuttings on the bit face to be covered with sticky formations, and hence reduces the drilling performance or even prevent it at all. This can be caused by many reasons, not only by formation behavior, but the major or the most important part is that once it happens, you need to solve or troubleshoot it as fast as possible because, again, time is your enemy in this situation. The longer you stay with this problem or the longer you leave bit bowling to accumulate, the harder it is to solve it later. And you will have to eventually pull out of hole to change the bit or clean it and rerun hole again, which will cause you a lot of MPT. So the cause of bit bowling may be due to formation behavior, it may be due to mud properties, it may be due to wrong selection of bit, or it may be due to wrong drilling practice. For the part of the formation, in case you are drilling in a reactive shale or reactive clay and you didn't add any inhibition or didn't add sufficient inhibition to your drilling fluid, it will cause you to have a bold bit. And in case of the inadequate mud properties, we are talking about any kind of properties that reflect the hole cleaning, like the mud rheology. In case of wrong bit selection, if you selected a bit that is not compatible with the formation, which means that the junk slot area is very narrow, which makes it very hard to be cleaned, or the cutter spacing is very narrow, which is also making it harder to clean between them. Also, choosing a bit with wrong nozzle size, meaning poor hydraulics, that will also be a reason for bit bowling. Finally, wrong drilling practice, which is reducing gallon per minute or reducing RPM and increasing ROP to above a specific threshold, causing bit bowling. There are many indicators that you need to take care of because once they happen, you need to take a step or you need to take an action because the longer you wait, the harder the problem will be. These indicators are decrease in drilling torque, sharp drop in ROP, and increase in pump pressure. Let's think together. If you had this bowling effect, you can't see any cutting structure. How you can drill? So of course you will not be able to drill efficiently. This is why you will find a drop in drilling torque because you are not drilling. And again, you will find a drop in ROP because you are not drilling. When it comes to increase in pump pressure, you can't also see any junk slot area. They are all blocked. And you can also see that some of the nozzles are also blocked, which causes an increase in pump pressure. So once you find one or more of these indicators, you need to pay close attention so that you can take an action fast. How we can prevent bit bowling from happening in the first place? it's easier to prevent it from happening than to cure it. And to prevent it from happening, you can do it using mud properties or using bit hydraulics or using drilling practices. When it comes to mud properties, you need to inhabit your drilling fluid if you are going to drill any kind of streaks of shale or clay, especially those which are reactive. And when it comes to bit selection, you need to optimize the nozzle size selection so that you can enhance and optimize the bit hydraulics so that you can enhance bit cleaning. When it comes to drilling practices, you need to increase the RPM, you need to increase the gallon per minute, of course, not to exceed the roadmap, and you need to reduce weight on bit and ROP in case you are in a formation that has higher probability of bit bowling. Finally, you can pump any pills containing surfactants or lubricants because they cause decreasing of the adhesion between the clay or the formation parts or the formation cuttings with the bit surface. Now let's say that the bowling happened already. How you can cure it? As we said, you need to be fast. You need to start pumping belts that can help you to remove this bowling. These belts has many types. For example, the lignosulfonate pill or the thinner pill. This thinner pill helps to deflocculate clay away from the surface of the bit. Second type is the caustic pill. The caustic pill is a pill which causes erosion of any cuttings. This pill can, if you add it to the drilling fluid and it had like any kind of bentonite or something, it can cause also some deflocculations. So the caustic pill here can help you to just clean the bed by erosion of the bowling out of its surface. You can also add some LCM. Yes, it's not the main function of the LCM. The main function is to cure the losses, but you can add it because the LCM itself, or some types of LCM like the nutshell, can cause the same erosion effect of the caustic pill and can help in eroding the cuttings away from the surface of the bed. Also, you can use detergent, which reduces adhesion of the clay to the bed and hence deflocculate it away from its surface. If these sweeps didn't work, you can perform a wiper trip to the nearest sand interval and start to maximize the RPM at this interval because the sand, as you can as you know, it has this erosion effect as well. So by maximizing the RPM at this interval, you are cleaning the bed from any kind of bowling on it. However, if you tried all these ways and it didn't you were not able to clean the bed, then eventually you will have to pull out of hole and either to clean the bed and rerun with it or replace it in case of a bad dull grading. So let's take 5 minutes break and be back so that we can continue the rest of the drilling problem. Now we are going to continue the rest of the problems in our presentation, starting with string washout. A string washout, my voice is clear, right?
Yes, engineer, it's clear.
Okay. String washout is simply a hole or rupture which happens in either the body of the drill string or the tool joints. This small hole, although it's just a small hole, it may result in multiple problems, starting with reduced hydraulics for the bed, since now we have a hole in the body or the tool string of the drill string, which may cause some part of the drilling fluid to exit from it and not to exit from the drill bit, and hence causing decrease in the ROP and causing bit bowling and other problems until it excessively reaches a full twist off, where part of the string is left in the hole and the other part is retrieved. It's parted into two parts. There are many reasons for washouts. It may be caused due to erosion. This erosion might be because of cuttings which exist in the drilling fluid because of poor solid control equipment that couldn't separate these cuttings and they were recirculated again inside the drill string, or it may be due to any kind of solids that are incompatible with the drill string that were added for any kind of remedial action or any kind of inhibition or any kind of giving a specific function to the drilling fluid. It may be also caused due to corrosion, which is a chemical reaction between the drilling fluid or between the formation fluids in case of a kick or between any kind of pelts you take and the drill string, where the drill string is incompatible with some pelts or properties of the drilling fluid, causing it to have this kind of holes. For example, if you are pumping an acid pill because of a stuck situation, this acid pill may cause you something like this. It may also happen due to mechanical damage, either because of harsh drilling environment, like too much vibrations, or due to rough handling by the drilling crew. It may also be due to defect in the material itself or poor inspection of the material. We need to identify how we can avoid it in the first place instead of troubleshooting it. Because even if you detected a washout, you will have to pull out of hole and replace this damaged part and rerun in hole again. So at the best case scenario, you are going also to have a lot of MPT. This is why we need to avoid it in the first place. And this is done by first checking the inspection report before running hole with the drill string. You need to make sure that everything is inspected, and we need to make routine and systematic inspection of each part that is running hole. You need also to mitigate drill string vibrations, which we are going to discuss later in this presentation. And you need to provide what is called WWI, which is written work instructions. This written work instructions needs to be provided by the operator or by the company man to the drilling crew so that they are not going to exceed any kind of limit at any point of their operation. This mitigation or this avoidance criteria is done during operation. However, you can also avoid it during planning phase 2. And this is by using torque and drag model, for example, to detect and to choose the well trajectory that will lead to the minimum drag and torque effects. It can also be represented in a good selection for the BHA during the planning phase, where you select a BHA with not so high stiffness so that it can so that it will be flexible with you in case you are drilling directional well or horizontal well. For a string washout, we need to detect it as fast as possible because there are so many instances that it takes only a few minutes for a washout to develop into a full and complete twist off. So the major and the main parameter that once you can see you will start to suspect that there is something wrong is the pump pressure. If the pump pressure has decreased with the same flow rate, especially, this is gradual drop. It's not sudden drop. I'm going to just correct it. So you need to check the pump pressure. If you found that the pump pressure is decreasing at the same flow rates, then this means that you may have a washout, especially if it's a gradual drop. You can also see other factors or other parameters that can increase the probability of the washout, which is reduced ROP and increase in flow return. Why is this? Because a part of the drill string, as we discussed, is exiting before the drill bit itself. Hence, this decreases the bit hydraulics because the amount of the drilling fluid that is exiting now is less, causing lower hydraulics and lower ROP. And since the drilling fluid is now exiting earlier, it may cause an increase in return flow rates. Also, you need to check if you have MWD in the drill string. Since the MWD is working on the base of an impeller rotating by the drilling fluid, if you have a washout above the MWD, then this means that the amount of the drilling fluid passing through the MWD has been decreased, which means that the amount of force that is pushing the impeller also decreased. so the impeller speed will also decrease. If the directional driller or if the MWD engineer found out that there is a decrease in the MWD impeller, then this also increases the probability of a washout that has happened in the string. So now let's see how we can act in such situation. If you found a drop in pump pressure, first thing is to stop rotation immediately and pick of bottom. You need to pick string of bottom and start investigating. And while investigating, you need to decrease flow rate because high flow rate can cause erosion of this of this washout that happened and causing it to develop into a twist off. So while investigating, you need to stop drilling, you need to stop rotating, you need to decrease the flow rate to the minimal accepted value. How you can investigate the problem? You need to check each specific part of your circulation system. This part starts from the mud tanks to the pumps to the surface lines to the drill string to the annulus. Starting with the tanks, you need to make sure that the mod engineer is or the derrick man are not adding anything to the active tank because some chemicals, if added to the active tank, may cause some fluctuations in the pump pressure. So you need to make sure that there is no adding in this part. If everything is cool on the tanks, then you start to move to the next point, which is the mud pumps. In order to check the mud pumps, you need to operate each pump separately and to see if both pumps are going to give you close pressure to each other or not. So if the pumps are effectively operating, you need to move on to the next point, which is the surface line. You need to isolate the surface line and start pressure testing it and check if the pressure is going to hold or not, and if there is going to be any visual leak or not. If the surface line is good, then you either have a problem in the drill string or in the annulus. In the drill string, it may be due to lost nozzle, so you need to make hydraulic run to check how much pressure you are going to lose if you had a lost nozzle from the bit. You need also to check the trend. If the trend is sudden, then most probably it's a lost nozzle. If it's gradual, then it's most probably a washout. When it comes to the annulus, you need to check if there is any kind of losses, has any kind of losses happened or not, because losses, as we discussed before, may be the reason for a decrease in pump pressure. You need also to check your background gases because if you had any kind of increase in background gas or any kind of increase in the bit volume, then this may be due to uh, an indication of a kick or a well control situation. So after investigating all these components, you will identify where the problem is. So if you identify that there is a problem in the string, and there is a washout that has been proved, then you will start to pull out of hole. And while pulling out of hole, keep the string wet, which means that you don't need to pump a slug pill because you need the string to be full of drilling fluid while you are pulling out of hole. Why is this? Because it helps you to detect the place at which the washout happened. If the string is full with mud, when you pull out of hole, you will find it leaking from the washout. However, if there is no mud here, some washouts are very small that cannot be detected by the eyes, so you will not be able to visually detect it. There are some reasons that you are not going to be sure whether it's because of a washout or not. And if you are in confusion, it's always safer to pull out of hole. You will lose time, you will lose MPT, but it's going to be better than losing multiple time or double of this MPT while trying to fish the lost string or while trying to sidetrack the well. The next problem is string twist off. And as we said before, string twist off is a full separation between the two parts of the string, causing one part to be retrieved and other to be left in hole. The causes of twist off are simply the same causes of washout, but more severe. We can also add fatigue failure. If you are drilling in a build-up section, you can see that a part of the string is under tension, while this part is under compression. Since the string is rotating, this part after 1 second will be in here, causing it to be under tension, while the part under tension is going to be here, where it will be subjected to compression. This continuous cycle of tension and compression causes fatigue of the string. It also may be due to over torquing or under torquing the string connection. Because if you under torqued the two connections together, they will separate. They may be separate under the harsh conditions of drilling. And if you over torque them, you may cause galling or damage to the thread, causing them to also separate. How to avoid the same way through which we can avoid a washout? You need to make regular inspection and to check the inspection report of each component before running hole. You need to apply torque and drag while modeling the well pour trajectory. You need to select BHE to give you not so high stiffness. You need to mitigate drill string vibrations. You need to provide work rating instructions. And also you need to make the correct makeup torque, not lower, not higher. Now let's discuss how we can detect the twist off. Of course, it's going to be detected easier than the regular washout because washout is just a rupture or a hole in the string, but here it's a complete separation. So you will find, first of all, you will find the drop in hook load and the drop in weight on bed. This is because you lost a part of the string. So you will find a part of the hook load not with you anymore. So you are going to lose a part of the hook load, which is equivalent to the weight of the lost part in hole. And we used the difference of the hook load before the event and after the event in knowing and localizing where you had the twist off. Because you know the weight of each component of your BHA, and you know from the hook load how much weight you lost. From here and from this and that, you can know what kind of BHA you lost even before you pull out of hole to the surface. You can also find a drop in pump pressure, and here it's sudden and it's high drop because almost 50% or even more of the pump pressure is lost in the nozzles of the bit. Since you lost the bit, you will find that the drilling fluid is exiting from this drill pipe, from this open-ended drill pipe. So you will find a huge drop in pressure. You will also find drop in ROB and weight on bit since you're no longer drilling, and you will find drop in torque since again you are no longer drilling. When it comes to troubleshooting, let's face it, it's not like the other problems because the major problem has happened anyway. You are not going to troubleshoot the twist off by retrieving the lost part at the same run because you already lost it. So the troubleshooting here is not how to troubleshoot the twist off as much as how not to increase the severity of the situation. You need not to increase the severity until you fish the ported string. And this is mainly by considering time as your enemy. Because the more you stay on this situation, the more cuttings in the well that are going to settle on the top of the fish or on the top of the twisted part or the twisted off part. If cuttings accumulated on this top, you will not be able to access it, so you will not be able to fish it. This is why you need to start preparing for fish tools even before pulling out of hole, so that it will be on site once you are out of hole. You need to spot a high vis pill on top of fish so that if any kind of cuttings are settling on the top of fish, the high vis is going to suspend them until you run in hole with the fishing equipment. Next problem is the nozzle plugging. Nozzle plugging is when any kind of foreign object enters into a nozzle, causing it to be partially or completely plugged, and hence reduces the available areas of flow out of the bit. This decreases the bit hydraulics. This reduces ROP. This may cause other problems like overheating, like bit damage, like bit bowling. There are many reasons for nozzle plugging. For example, nozzles related to mud, nozzles related to poor selection of nozzles, or reasons related to uh, any kind of foreign objects that entered. In all of them, you have a foreign object that entered the nozzle. So these kind of foreign objects can be like a junk that you drilled and a part of it has got stuck in a nozzle. It can be solid cuttings that has been recirculated again with you in the drilling fluid because of poor handling equipment. It can be due to pumping LCM or pumping any kind of solids that are incompatible with these nozzle sizes. In order to prevent this, you need to make sure that your solid control equipment are operating effectively so that you will not recirculate cuttings again in the drilling fluid. You need to make sure that you have nozzles large enough for the type of drilling fluid that you are using and the type of formations that you are drilling. And you need to make sure that the LCM sizes are compatible with the nozzle size that you are using. If you want to pump LCM, which is of larger size than these nozzles, you need to use what is called PPL sub or circulating sub. PPL sub is short for pressure bypass locking sub because it causes bypassing of the original path of the drilling fluid into the bit and out into the annulus by opening ports in the side of the string and hence allowing you to circulate the drilling fluid without having to pass it through the drilling bit. And hence you can protect your nozzles and the other sensitive components in the BHA from being plugged from large solid particles like the one exists in the LCM sweeps. Next problem is vibrations. Vibrations are oscillations that mechanically affect the drill string. There are three major types of vibrations. They can happen alone or they can happen combined with each other. These vibrations are axial, lateral, and stick slip. For the axial vibration, which is also called bit bouncing, and as the name implies, it's because the bit keeps bouncing, it keeps going up and down, it keeps engaging and disengaging with the formation. And this is indicated by erratic weight on bit that you can see. It can also affect bit mainly by breaking its cutters, and it may even causing erosion of its blades. The way through which you can troubleshoot this type of vibrations is by increasing weight on bit and decrease RPM, because this is how you can make it more stabilized by pushing higher weight on bit on the bit, which causes it to be more stable on its position. The second type of vibrations is lateral vibrations, which is side-to-side motion, which causes the drill string to keep hitting the sides of the well bore. The lateral vibrations are considered as the worst kind of vibrations because it has the highest detrimental effects on the drill string. It can cause BHA damage, it can cause twist offs, and it even causes hole irregularities and hole washout. The solution for it is the same solution as the bit bouncing, which is increasing weight of bit and decreasing RPM. For the third type, which is the stick slip vibrations, it's a continuous cycle of stick and slip, as the name implies. The drill string stick into the formation, causing the RPM and the torque to drop, then suddenly releases and slip, causing very fast RPM and very high torque cycles. So you have fluctuating cycles of high, low torque and fluctuating cycles of high, low RPM. This also causes twist offs, and it's detrimental when it comes to downhole BHA tools. It can also cause the occurrence of ledges in the well borer. The solution of the stick slip is opposite to the other two types, which is decreasing weight of bit and increasing RPM. These mitigation are only by controlling the drilling parameters. However, you can use other subs or other accessories that can dampen these vibrations, like shock subs and like anti-stick slip subs. These subs can reduce and dampen these vibrations without having to control your drilling parameters. Next problem is the ballooning effect. The ballooning effect is simply a trend of losses when you operate the pump, and once you shut off the pump, you have gain. This is because you are drilling in a naturally fractured formations. If you remember what we talked about previously in the difference between the mud weight and the ECD, you will understand this phenomena clearly. Because when you operate the pump, you have the ECD, which is higher than the mud weight. This ECD exceeds the fracture pressure, causing to open these fractures inside the formation and causing losses. When you shut off the pump, you lose the ECD, causing you to have only the mud weight affecting the formations. So the formation start to close the fractures again and causing flow back of the drilling fluid that they took before back into the well. So how you can detect it, simply by monitoring the pit level or the mud tanks. If you have losses while pump is on, followed by gain while the pump is off, with this gain declining with time, then this means that you have ballooning effect. For the troubleshooting of this problem, you just need to try to reduce the ECD. Don't reduce the mud weight. The problem is with the ECD. You need to reduce the flow rate. And if you have a window of reducing mud weight without like falling below the pore pressure, you can do it. But the main problem is with the ECD itself. So it's better troubleshooted with decrease in flow rates. Reaching to the final drilling problem, which is the well control problems. And don't worry, I know that it's a huge topic, but we are just going to scratch it from the surface. So for the well control or the well control problems are mainly due to the entry of an influx into the well bore. This influx is formation fluid that managed to enter the well bore due to pore pressure being higher than hydrostatic pressure. So we have two type of kicks. Once that happens during drilling and once that happens during trapping. For those who which happens during drilling, this is simply because the pore pressure is higher than the hydrostatic pressure, either because your hydrostatic pressure is low or because the pore pressure is high. And we will discuss this part in the causes in the next slide. While when it comes to swapped kick, it's because mainly you are pulling out too fast, causing suction or vacuum effect. Same as when you pull a medicine with a syringe, this vacuum that you do with it is the same exact swapping effect that happens when you pull out of hole too fast with a drill string. So when it comes to the causes, the drilling kick, as we said, we have pore pressure higher than the hydrostatic pressure. So either you have mud weight, which is low, you have hydrostatic head or the TVD, which is low, or you have the pore pressure, which is high. In case the mud weight is low, this might be because you miscalculated the mud weight or because you didn't monitor the mud weight closely, which caused it to be cut by background gases, causing it to decrease since it's now entrained with gases. So it decreased, causing the mud weight to be lower. When it comes to the hydrostatic head itself, if you have complete loss, then this will cause drop in the head itself and hence will cause a drop in hydrostatic pressure. However, if the pore pressure is the one which is high, then it's just an abnormal pressure zone. There is nothing wrong with your hydrostatic fluid or your drilling fluid, but you just encountered an abnormal pressure zone. And as the name implies, it's abnormal. When it comes to swap kicks, as we said, it's because of this vacuum that you made while you were pulling out of hole. So it may be because you are pulling out of hole too fast, or because the drilling fluid itself is very viscous, or the clearance between the drilling string and the annulus is very narrow. How we can detect it? We have two measures of detecting a well control situation. First one is what is called kick warning sign. Second one is called kick warning indicator. And now we will differentiate between them. For the kick warning sign, it's something that tells you that you might have a well control issue. These signs are fast drilling break, which means that the ROP increases because in abnormal pressure zones, you have more fluid contained and pressurized in them. And by more fluid, we mean more pore spaces and more pore volume, which means that it's more drillable. This is why the ROP is faster. Also, you will notice decrease in pump pressure since the influx has lower weight than the drilling fluid. You also will notice large splintered cuttings on shaker because as the drilling fluid hydrostatic pressure decreases, the well bore will start to cave in, causing splintered large cuttings to appear. You will find also if you are in a trap that the hole is not taking the correct displacement volume. So if you are pulling out of hole wet, then the displacement volume is going to be the closed end displacement. If you are pulling out of hole dry, then it will be just the metal displacement. So if you just pull out of hole like 5 stands and you are supposed to fill the well with 3.5 barrels, but you filled it with 2 barrels, this means that 1.5 barrels have been filled by the formation. Also, an increase in background gases, because increasing gas is always an indication of probable well control situation. Also, the presence of connection gases, because as you remember from the comparison between ECD and the mud weight, a connection gas happens when you are making a connection, which means that the pump is off. So when the pump is on, you have ECD on your side, so you are overbalanced. But when the pump is off, you only have the mud weight, which means that this difference makes the mud weight itself on its own lower than the pore pressure, causing gases to enter while the pump is off when you are making a connection. When you find one of these warning signs, it doesn't mean that you go straight and shut in the well. This is not right. If you have warning sign, then you need first to detect if it's going to be a well-controlled situation or not. And to verify this, you need to verify it by stopping operation and making what is called flow check. A flow check is stopping the pump and checking if you are going to have any returns. If there are no returns, then the flow check is negative. Then you need to circulate bottom up so that if anything happened or if any influx entered the well, it's going to appear when we circulated bottom up. So that if we circulated the bottom up and it's completely clear without any kind of influx, then we don't have a well controlled situation. We can continue drilling. On the other side, the kick warning indicators are strong indicators that tells you that you already have a well controlled situation, not just a sign. These indicators are increase in the mud volume or the tank volume, because of course you have an influx which will displace an equal volume of it into the tanks. Increase in return flow rate, because something is helping you, like something is helping your pump. The pump is circulating with 600 gallon per minute and you have another pump downhole, which is the formation. So you will find an increase in return flow rates. Also, a flow with pumps off, because if the pump is off, you are not supposed to have any return other than the fingerprint. Once the pump fingerprint, which is the amount of fluid that returns after the pump is off, is done, you are not supposed to have any kind of return. So if you are having continuous return, then you are having a kick warning indicator. Unlike the kick warning signs, which we had to check first before shutting in the well, if you had one indicator, then you go immediately and shut in the well without verification, because these are already verifications that you have a well-controlled situation. So once you have one kick warning indicator, immediately shut in the well and prepare for killing the well. Killing the well is done by many methods, but they are out of the scope of this session. And if you want to go deeper in them, they are going to be covered in next week's course. Finally, how you can prevent such occurrence from happening. This is done by keeping your hydrostatic pressure above the formation pressure. And this is done by keeping the mud weight sufficient, by accurate calculations, and by close monitoring to prevent it from being cut by background gases. Also by keeping the hole full so that you can keep the hydrostatic head. So in case you had any kind of lost circulation, any kind of complete lost circulation, you need to cure it before continue drilling. And you need also to stay away from abnormal pressure zones, which are normally associated with some problematic geologic structures like folds and faults. It's always like more wise to drill directional wells in case there is nothing to prevent this, so that you can just get away from these problematic structures that may cause you to encounter an abnormal pressure zone. And when it comes to trapping, you need to use swap and surge model, because this swap and surge model will identify the clearance between the drill string and the annulus and the hole size, and it's going also to take into account the type of mud that you are using, so that it's going to give you an output of the tripping speed that you need not to exceed. So if you are pulling out of hole, you will not swap the well, and if you are running in hole, you are not going to surge the well, causing fracturing and dropping in the hydrostatic head. So you need to stick to this model to prevent any kind of problems related to well control situations. So that was the end for our session today. I hope you found it beneficial, and I hope that it added to your value. Now I think we have time for Q&A. Okay, the first question is asking, would you recommend closing the pipe rams and flow through the annular to find a wash? I believe you mean to find a washout. If this is what you mean, I can't find the relevance. We close the pipe rams mainly for well control situations. Uh, and if you are trying to say that you are going to pressure test your system, like closing the annular or the pipe ram and start pressurizing your system and pressure test the full system to check its integrity, then it's not mandatory that it's going you to give you an indication that you have a washout. Since if you have any losses and you're not encasing, it may be due to losses to the formation. You may be fracturing a formation, not you're having a washout. So the safest way through which you can check is by isolating each part of your system and checking if it's going to be the problem from it or not. Same as we said before, checking your mud tanks, checking your surface lines, checking your drill string, checking your annulus. Um, could you explain again the key seating problem? Okay, let me return back. So the key seating problem here, you can see this from a top view. This is a top view of the well. You can see that this is the main well bore. It's supposed to be only this circle. However, you have this microcircle next to it. This microcircle is because you have severe dogleg. A dogleg is a sharp change in the inclination of the well, which is higher than 3 degrees per 100 feet. If you have this severe dogleg, this may cause the BHA while drilling to be pushed to the side of the wellbore, causing it to erode this micro hole in soft formations. Now you have this main hole and this micro hole. When you start pulling out of hole, this tool joint has larger OD than the rest of the drill string. When it's starting pull out of hole, it will enter into this micro hole. And while it tries to pull out of it, it will get jammed into its side, causing it to be stuck. The geometric problems happen only in wildcats, not necessarily. As we said, we have three types of well-pour geometry: the key seating, the ledge sticking, the tight hole. So the key seating and the ledge sticking are dependent on the lithology, not in case you know it or not. If you have a lithology of varying soft and hard formations, and if you have sharp changes in sharp unintended changes, not in the direction plan in the well path, then this most probably is going to give you problems with key seating and ledge sticking. And when it comes to tight hole, it's because your bed has gone under gauged. Any bed is susceptible to getting worn out, so it's not only related to wildcats. Uh, okay, we done it twice where the top drive was disconnected from the pipe and we noticed the backflow through the stump. Okay, the backflow here is due to either a well control situation or due to a YouTube effect. But how is it related to washout? Yes, push out in the pipe, exactly. So I don't find the relevance. But anyway, let's connect on WhatsApp so that I can understand better what you mean because I don't find the relevance here. You can see my contact information in here. You can tell me exactly what you mean, and I can further discuss with you this point. So I can't see any more questions. In bit bold, the torque increases. No, the torque decreases. The torque decreases, the ROB decreases, and the pump pressure is the only factor that is increasing. Because in bit bowling, you are covering the cutting structure. So you are not drilling, which means that you don't have ROP and the torque is low since the torque is a reaction of drilling. Okay, I can't find any more questions. If there are any further questions that you can bit bold causes stacking? Yes, exactly, because bit bowling increases the OD of the string. If you have a stabilizer which is 7¼ inch, after bowling it's going to be 7.5 inch. So you are having tight hole. It may cause stacking. So if you have any other questions, reach me on this number on WhatsApp, and I will be more than glad to answer your questions. I would like to thank you for attending this session. And again, I hope it was beneficial for you. If you wanted to dig deeper in any of the topics that we talked about today, feel free to register for the course that is provided by OPA. I believe they have given you the link. I hope to see you there. Thank you so much for attending this session and see you soon. Thank you and goodbye.
Thank you very much for this amazing webinar, Engineer Saif.